SimphoSOFT is uniquely suited to simulate multiphoton absorber molecules since it is faster and more accurate than conventional techniques. This video includes a summary of SimphoSOFT benefits, example applications for multiphoton materials, and example molecule types. We will show a detailed example of using SimphoSOFT for modeling optical limiting. We will also briefly mention Z-scan data fitting and modeling for 2-photon absorber and 3-photon absorber molecules, and briefly describe the SimphoSOFT multiphoton absorber database. Some of the many benefits of using SimphoSOFT to model multiphoton absorbers are listed here. In contrast to conventional methods, SimphoSOFT provides complete molecular and light propagation models to ensure fast, accurate simulations. From the simulations, you will better understand the effects of optical limiting, saturation, excited state absorption, and adding additional energy levels to the model. There is no need to write new software code when higher excited states are reached. Extra energy levels and transitions can be added easily, and the program automatically adjusts the mathematical model for the new information. Solutions are calculated using a complete numerical model with no analytical approximations. In addition, you will save significant amounts of time by doing virtual experiments on the computer rather than time-consuming lab work. SimphoSOFT allows you to model Z-scan experiments and to fit Z-scan data to determine 2-photon and 3-photon absorption cross-sections. Finally, a newly developed database of over 1,100 multiphoton absorbers speeds your work by reducing the time needed to do background searches of scientific publications. 3 example applications of multiphoton absorbers are shown here. 2-photon absorbers are used for optical limiting and protection from lasers, since 2-photon absorption depends on the square of the light intensity. Significant amounts of absorption occur only at high incident intensities where optical damage may occur to unprotected eyes and sensors. 2-photon absorbers are also used as molecular probes for biological tissues. The reason that 2-photon absorbers are used is that the longer excitation wavelengths of 2-photon absorbers can penetrate more deeply into tissue than shorter single-photon excitation wavelengths. 2-photon absorbers can also be used for high-resolution 3D lithography, since the interaction volume for 2-photon absorption is much smaller than the interaction volume for single-photon absorption. This results in higher resolution. Examples of multiphoton absorbers are organic molecules that are photoactive, including fluorescent dyes, phthalocyanines, porphyrins, organometallic molecules, and quantum dots. We will show how to use SimphoSOFT to model 2-photon absorption and optical limiting in AF455 molecules. SimphoSOFT is ideal for testing different models to see what works best. The structure of AF455 is shown here. This example is taken from a Photonics West 2012 paper. First, we will do simulations doing a 5-level model. Then we will show how easy it is to add a 6th energy level and new transitions in order to get a better fit to the experimental data. We now go to the SimphoSOFT program, which we have already opened to an AF455 project. The experimental CAD diagram shows a laser beam and a sample. Selecting Beam Properties opens a Beam Properties dialog. Opening the Sample Properties dialog, we have set the sample thickness and the AF455 concentration. Next, we select Materials CAD or MCAD to view the energy level diagram. We also open the Partial Differential Equations panel to show the rate equations. We change the coefficient form to symbolic. We start with a 5-level diagram with 3 singlet states and 2 triplet states. The 5 energy levels correspond to 5 rate equations on the bottom panel. The red transition from state S0 to S1 is 2-photon absorption. The cross-section is 8 times 10 to the minus 21 centimeters fourth per gigawatt. The other 2 red transitions are 1-photon absorptions. The blue and orange transitions are relaxations, where the orange transition from state 1 to state 3 is intersystem crossing from the singlet state manifold to the triplet state manifold. We will run a simulation with these 5 levels and then later show how easy it is to add more levels if needed. In Run Configuration, type should be set to Series. In the Series tab, we insert a new line to do a series of runs where we vary the pulse energy. We insert values 0.01, 1, and 35 in units of microjoules. To start a simulation, we go to the Project menu and choose Run Simulation. The program does 3 simulations for the 3 energy level values. The transmission results are listed in the summary. Here is the summary list. Here I reproduce the plot from the Photonics West paper. The first 2 points that we have just calculated at energies 0.01 microjoule and 1 microjoule are shown as crosses and fit the data that was done at the Air Force Research Lab. The 35 microjoule cross is on the blue dotted line and higher than the experimental value at 35 microjoules. An expanded view is shown in the box to make it easier to see the deviation. Notice that the sample is highly transparent with high transmission at low pulse energies, but becomes highly absorbing at high energies. This is a typical response for 2-photon absorption and optical limiting. We now go back to the SimphoSOFT program and show how easy it is to add more energy levels. First, we add a 6th level. This is labeled level 5 since the numbering starts at 0. We have placed it above singlet level 2 and we specify its properties. Next, we add 1 photon absorption from the S2 level to the S5 level. And we set its properties. Finally, we add relaxation back to the S2 level. And we set its properties. We set its relaxation time to 160 femtoseconds. The simulation model is automatically updated, and the new extra terms are shown in the partial differential equation panel. We now rerun the simulation with the new energy level and new transitions. The results are again shown in the summary. The results at 0.01 microjoule and 1 microjoule are essentially unchanged, but the transmission at 35 microjoules has decreased from 0.171 to 0.124. From this example, you can see that SimphoSOFT allows you to quickly change the model or model parameters and try out different ideas. Going back to the plot, we see that the new value of 0.124 for the transmission at 35 microjoules is a much better fit to the experimental data. SimphoSOFT can also do other types of simulations for multiphoton absorbers. For example, in order to determine 2-photon absorber and 3-photon absorber cross-sections, open aperture Z-scan experiments are normally done. Please see the Z-scan video for more details about Z-scan fitting and modeling. To illustrate Z-scan, a schematic diagram of an open aperture Z-scan experiment is shown here. In order to determine the 2-photon absorber or 3-photon absorber cross-section, SimphoSOFT can take the Z-scan experimental data and can do a least squares fit to a molecular model having 2 or more energy levels. SimphoSOFT can also do general Z-scan modeling to illustrate what happens, for example, if the molecule has 3 or more energy levels and the incident pulse energy is high enough to populate more than the first excited state. Symphotech is also selling a multiphoton absorber material database listing properties of over 1,100 molecules. The database includes key properties such as structure, energy level diagram, and optical parameters such as the 1 PA, 2 PA, and 3 PA absorption cross-sections, as well as fluorescence decay times. From the database, you can find and compare materials that meet the specifications for your application and to improve performance. We have done extensive literature searching for you, saving you time and effort. In summary, we have demonstrated the capability of SimphoSOFT to achieve fast, accurate multiphoton absorber simulations over a wide range of conditions. SimphoSOFT has an easy-to-use graphical user interface to set up an unlimited number of energy levels and visualize the results. And finally, we have produced a multiphoton absorber database with over 1,100 MPa molecules and their photophysical parameters that will save you time and speed up your material development.